You. Hi, everyone. Thanks for coming. Today we have Carlos Díaz-Ramos, who will tell us about cohomogeneity 1 actions on quaternionic hyperbolic spaces. So feel free to start whenever you're ready.
Okay, so thank you very much for the invitation to this seminar. I would like to talk about a recent paper in collaboration with Miguel Domínguez Vázquez and Alberto Rodríguez Vázquez about the classification of homogeneous hypersurfaces in quaternionic hyperbolic spaces, which completes the classification of homogeneous hypersurfaces in rank 1 symmetric spacers. And we obtain, as a byproduct, a family of uncountably many inhomogeneous isoparametric hypersurfaces with constant principal curvatures in the quaternionic hyperbolic space. So the idea of this talk is first to recall some basic stuff about cohomogeneity 1 actions, the classification of homogeneous hypersurfaces in symmetric spaces of rank 1, and then I will talk about the quaternionic hyperbolic case, basically focusing on the ideas behind the proof of this classification. So a few basic notions, like the notion of cohomogeneity 1 action. So we say that a Lie group acting isometrically on a Riemannian manifold is of cohomogeneity 1 if its principal orbits are hypersurfaces. By principal orbits, we mean orbits whose isotropy is as small as possible. And we will always assume in this talk that the group acting upon the manifold is connected and closed, which means that the action is proper, orbits are closed and embedded, and isotropy groups are compact. All of this provided that M is connected and complete and so on. Principal orbits of a cohomogeneity 1 action are also called homogeneous hypersurfaces. And we say that two cohomogeneity 1 actions, or in general, two isometric actions, are orbit equivalent if there is an isometry of the ambient manifold that maps the orbits of one action to the orbits of the other action. One of my basic problems in research is to classify cohomogeneity 1 actions or polar actions, or in general isometric actions up to orbit equivalence. This means that I am not so much interested in the group acting or in how it acts, but only on the orbits it produces. All of this up to orbit equivalence, or if we think of homogeneous hypersurfaces up to congruence in the isometry group of the ambient manifold. And the second problem that I am interested in is the characterization of homogeneous hypersurfaces, or more generally, homogeneous submanifolds using geometric data. We will see a couple of examples of geometric criteria that can be used to classify or to characterize homogeneous submanifolds. So the classification of cohomogeneity 1 actions in Euclidean spaces was obtained many years ago by Somigliana, Levi-Civita, and Segre. They proved that there are basically three examples: concentric spheres around a point, parallel hyperplanes, parallel affine hyperplanes, and tubes around an affine subspace. In the case of the three-dimensional case, these are the usual cylinders. In the general case, the axis can be any affine subspace, and we get somehow a generalization of a cylinder in higher dimensions. For real hyperbolic spaces, the classification was obtained by Cartan in his study of isoparametric hypersurfaces in spaces of constant curvatures. There are basically four families: geodesic spheres, again, tubes around totally geodesic real hyperbolic spaces of codimension greater than 1. Because if the codimension is exactly 1, then we have a foliation. There are no singular orbits. and we get a real hyperbolic space of codimension 1 and all its equidistant hypersurfaces. And then there is a curious example, which is called the holosphere foliation, which is a way of embedding parallel Euclidean spaces in a totally umbilical way inside the real hyperbolic space. The classification in spheres was obtained quite a bit later by Xiang and Lawson, and basically the result can be summarized as follows. Homogeneity 1 action on a sphere is orbit equivalent to the isotropy representation of a symmetric space of rank 2. Symmetric spaces have been classified, their isotropy representations are known, so just looking at a list and doing some calculations, one can get the full classification of homogeneity 1 actions in spheres. For the complex projective space, there is a very similar result, except that in this case, we have to take isotropy representations of Hermitian symmetric spaces of rank 2 and take a quotient. A Hermitian symmetric space of rank 2 is endowed with a complex structure, so its tangent space at a point is basically a complex vector space. It can be proved that the isotropy representation of such a space is polar. Its section is totally real. And if we projectivize this complex vector space, then we get homogeneity 1 action in the corresponding complex projective space. Takagi's result asserts that this way of getting homogeneity 1 actions is everything that we can get up to orbit equivalence. The classification in complex hyperbolic spaces was obtained by Bernd and Tamaru around 2005 or so. There are typical examples like tubes around totally geodesic complex hyperbolic spaces, tubes around a totally geodesic real hyperbolic space of dimension n, and holospheres, just as in the real hyperbolic case. But then it was found that there is a homogeneous minimal hypersurface in the complex hyperbolic space. This was found by Longhar in his PhD thesis, and all its equidistant hypersurfaces are also homogeneous. This was an unexpected example at the moment. And Bernd and Brook went to generalize this construction to a ruled minimal homogeneous submanifold whose tubes are also homogeneous hypersurfaces. The construction is similar to Longhar hypersurface, except that the codimension is greater than 1. And well, there is a parameter phi, which is related to something called Keller angle, which I will discuss a little bit later. In the quaternionic projective space, it's quite easy to generalize Xiang and Lawson and Takagi's result. It turns out that in this case, the two examples that appear, or the two families that appear, are also related to symmetric spaces of rank 2, but they can be explained more easily, saying that they are just tubes around total geodesic quaternionic projective spaces and tubes around a total geodesic complex projective space of dimension n. Then in the Cayley projective plane, there are exactly two actions up to orbit equivalence, the action of spin 9 and the sp3 times sp1. And in the non-compact counterpart, the result was obtained by Bernd and Tamaru as well. There are also typical examples like geodesic spheres, tubes around a totally geodesic octonionic line, tubes around a totally geodesic quaternionic hyperbolic plane. This is the holosphere foliation, which is somehow analogous to what we discussed before for real and complex hyperbolic spaces. This is a solvable foliation, which we will discuss later, but it's basically related to the Longhar hypersurface. And then there are like 5 more families, which are generalizations of the Bernd-Brook construction, which I won't explain here, but they can be found in this paper by Bernd and Tamaru. Actually, this paper by Bernd and Tamaru basically tried to classify homogeneous hypersurfaces in symmetric spaces of rank 1 and of non-compact type, but they didn't succeed in the quaternionic hyperbolic space, which is basically the topic of this talk.
Sorry, can I ask a question?
Yes, of course.
Which of these come from like the isotropic representations of rank 2 Wolf spaces?
You mean in the Cayley hyperbolic plane?
I thought more about the Quaternion projective case. So like we had this similar thing that we can look at the isotropic representations of
yes.
Rank 2 Hermitian symmetric spaces, and I think we can do the similar thing for like Wolf spaces, right, of rank 2.
So in the Quaternionic hyperbolic space, projective space, it's exactly the same theorem as for the complex and the real projective cases. So they come from isotropy representations of symmetric spaces of rank 2, except that here the symmetric space must be a product of quaternionic. It has to be a quaternionic symmetric space of rank 2 or a product of 2 quaternionic symmetric spaces of rank 1. So the first case corresponds to tubes around a totally geodesic complex projective space, and the second case corresponds to tubes around the totally geodesic hyperbolic projective spaces of lower dimension.
Okay, thank you.
So it's exactly the same theorem, except that the situation is very simple, and you can phrase it as tubes around totally geodesic things.
Okay, thanks.
Okay. So coming back to the quaternionic hyperbolic space, this is a symmetric space that can be written as the quotient of sp1n over sp1 times spn. As it is the case for any symmetric space of non-compact type, its isotropy group can be decomposed as a topological product of the isotropy group at a point, which is compact, an abelian subgroup, which in this case is one-dimensional because it is a symmetric space of rank 1. Basically, this group fixes a geodesic through the origin, where by origin I mean the point that is fixed by the isotropy group. And then there is a nilpotent group, which I will describe a little bit further in the following slide. And this produces something similar to the horosphere foliation that we discussed in the real hyperbolic space. So the thing is that this decomposition is not a product of Lie groups, but AN is a semi-direct product. And moreover, it can be proved that this solvable part, so A is abelian, N is nilpotent, this semi-direct product is therefore solvable. This solvable part of the Iwasawa decomposition acts transitively on the quaternionic hyperbolic space. This is actually true for any symmetric space of non-compact type. And therefore, any symmetric space of non-compact type, in particular this one, can be seen as a solvable Lie group endowed with a suitable left invariant Riemannian metric. The nilpotent part of this Iwasawa decomposition is actually a two-step nilpotent Lie algebra, whose center is three-dimensional, and it can be interpreted or identified as the imaginary part of the quaternions. And its orthogonal complement is a quaternionic hyperbolic space. The brackets can be described explicitly. So basically we have to say what is the bracket of an element of G alpha with itself because everything else is basically zero. By the way, this alpha is a so-called simple root of a root space decomposition of the Lie algebra of the group of the isometry group of the quaternionic hyperbolic space. There's only one positive simple root because the rank is 1. And this is a symmetric space of BC1 type. So there's 2 alpha is also a root. And as I was saying, the bracket of 2 elements in G alpha is an element of D2 alpha, which can be recovered in the following way. Here Z is an element of D2 alpha, and basically the bracket is related to a complex structure, which is obtained seeing G2 alpha as a Clifford module acting on this space G alpha. And this is the reason why G alpha becomes a quaternionic vector space. Then the bracket of the abelian part A with the elements in N is basically the identity. It's half the identity in G alpha and the identity in G2 alpha up to rescaling by the metric. So the strategy to find the classification of cohomogeneity one actions on symmetric spaces of non-compact type is based on the following theorem, which was proved by Mostert in the complex case and by Bergerie in the general case. This theorem asserts that if we have a cohomogeneity one action, a Riemannian manifold, it has to be connected and complete and so on, then its orbit space is homeomorphic to a manifold of dimension 1 with boundary. Actually, it can be seen that if our ambient manifold is a Hadamard manifold, only 2 of these possibilities can arise. The first one corresponds to cohomogeneity one actions with no singular orbits. Actually, I didn't say that, but the boundary points of these manifolds, these one-dimensional manifolds, correspond precisely to the singular or exceptional orbits. So in the first case, there are no singular orbits. In the second case, there's one boundary point which corresponds to the singular orbit. So there is either no singular orbit or one singular orbit. And the procedure devised by Bert and Tamaru consists of first studying singular orbits which are totally geodesic, and then the general case or the generic case when the singular orbit is not totally geodesic. It was a surprise at the moment to find examples with non-totally geodesic singular orbits, although nowadays I think it is more or less assumed that it's not so difficult to find such examples. So turning our attention to the case of cohomogeneity one actions with no singular orbits, it can be shown that in a symmetric space of non-compact type, there are exactly 2 possibilities. One of them is the horosphere foliation, which is the action of the nilpotent part of the Iwasawa decomposition that we described before. And the second possibility is called the solvable foliation, which is basically in our description before of our symmetric space as solvable Lie group. We have to remove a line in the G alpha part that we described before. So in this decomposition, we remove a line in G alpha, and this produces a foliation, which is called the solvable foliation. In the real hyperbolic space, this is exactly the foliation consisting of equidistant hypersurfaces to a totally geodesic real hyperbolic space of codimension 1. But in the rest of the symmetric spaces, it's something different, partly because there can be no totally geodesic hypersurfaces in symmetric spaces other than the ones that have constant curvature. So these are basically very well known. So our study of actions with no singular orbits stops here. And it's equally easy to classify actions with one totally geodesic singular orbit, at least in the quaternionic hyperbolic space. In general symmetric spaces of non-compact type, the problem is more involved, but in this particular setting, it's rather easy because totally geodesic submanifolds of quaternionic hyperbolic spaces are known. So we just have to figure out in which case tubes around them are homogeneous. And this depends basically on the fact that the isometries are quaternionic and that the normal space to that totally geodesic submanifold must behave correctly with respect to this property. So basically this means that the normal space has to be quaternionic, totally complex or totally real, and it turns out that this is only satisfied when the totally geodesic submanifold is a quaternionic hyperbolic space or a complex hyperbolic space of dimension exactly n. In all other cases, the normal bundle splits as sums of other things, and the isometry group cannot act transitively on the unit sphere of the normal bundle. So these are the only examples that arise as homogeneity one actions with one totally geodesic singular orbit. So the difficult situation is, of course, when the action has a singular orbit, which is not totally geodesic. And in this case, Bernd and Tamaro gave a procedure to construct such examples. In order to explain this procedure, first we need to define the subgroup K0. This is a subgroup of the isotropy group, which fixes the maximal abelian, the abelian part of the Iwasawa decomposition. Okay, it's exactly the normalizer of that abelian part of the Iwasawa decomposition in the isotropy group. Turns out to be isomorphic to SP1 times SPn minus 1. And we can think of it as the subgroup of K that fixes this foliation. This is a foliation of one-dimensional lines. One of them is a geodesic, and the rest are equidistant curves to this one. This geodesic has two boundary points, this one, and basically K0 is an isometric action that somehow scrambles all these curves. We have to take into account that the isometries of K0 have to be quaternionic, so not anything is possible, and this is why it turns out to be isomorphic to SP1 times SPn minus 1. K0 acts on G alpha, which is a quaternionic vector space, basically in the usual way, in the canonical way that we would expect. And the Bernd and Tamaro result says that considering the composition that we had before, if we now take a subspace of G alpha, such that its normalizer in K0 acts transitively in the unit sphere of its normal space, then the group whose Lie algebra is this one. So we take A, this subspace of G alpha, G2 alpha, and its normalizer in K0, the normalizer of W in K0. Then it can be proved that the corresponding group acts with homogeneity 1 on the quaternionic hyperbolic space. This is actually a general construction for symmetric spaces of rank 1 and non-compact type. And they used this theorem to get the classification in the real, complex, and the octonionic hyperbolic spaces, but they didn't succeed in the quaternionic hyperbolic space, which is basically the aim of this talk. In order to fix notation, then, we will call a subspace satisfying this condition proto-homogeneous. Namely, we will say that a subspace of a quaternionic vector space is proto-homogeneous if its normalizer in SP1, SPn acts transitively on the unit sphere. So basically, the rest of the talk is to classify proto-homogeneous subspaces in quaternionic vector spaces, because from Bernd and Tamariu's theorem, this will imply the classification of cohomogeneity one actions in quaternionic hyperbolic spaces. Okay, so this is the problem that we are going to handle from now on. So the first thing that we will do is to find the geometric invariance of proto-homogeneous subspaces of a quaternionic vector space. A quaternionic vector space can be seen as a real vector space endowed with a quaternionic structure. So this is a three-dimensional vector space where we can pick three orthogonal complex structures satisfying the product relations of the quaternions. The Keller angle of a vector small v in a subspace capital V of a quaternionic vector space with respect to a complex structure is by definition the angle between J of small v and the subspace. This can be defined algebraically like this in an equivalent way. So we look at the square length of the projection of J of V, and what we basically call cos square of the angle that produces this projection, the Keller angle of V with respect to J. And then we define the so-called quaternionic Keller angle of a vector V. So we have a definition of Keller angle with respect to a quaternionic, with respect to a complex structure. So the quaternionic Keller angle is a triple. There are three Keller angles with respect to a canonical basis, so a basis satisfying these conditions above, in such a way that each element of this triple is a Keller angle with respect to the corresponding element of the canonical basis, and also satisfying the condition that this equality must hold. Another way of understanding this, which is probably a little bit easier, although I don't know, is the following. We consider the following bilinear form. We take a pair of complex structures in the quaternionic structure, and we look at the square of, at the inner product of the projection onto V of JV and J prime V. It's easy to see that this map is bilinear and symmetric, and therefore by the spectral theorem, it can be diagonalized with real eigenvalues. These eigenvalues up to multiplication by the square norm of V are bounded by 1, so they can be written as the cos square of a number between 0 and pi over 2, and this is precisely what this number is precisely what we call the each of the elements of the triple of the quaternionic Keller angle. So the moral here is the following: we have this symmetric bilinear form, which can be diagonalized, and the elements of the diagonal are basically the Keller angles, and the eigenvalues are the canonical basis that somehow appears in this definition here. So basically what we have to keep in mind is that each subspace of a quaternionic vector space can be defined a triple, which is a triple of angles with respect to a canonical basis, and this depends on the vector that we choose in this space. Okay, so it's like a triple of angles related to a quaternionic structure. Since we are assuming that our subspaces are proto-homogeneous, it can be proved quite easily that the quaternionic Keller of this proto-homogeneous subspace is constant. which means that it doesn't depend on the vector v that I have choose to define it. So this is a property that we are going to exploit quite a lot for our classification, because it is a geometric invariant of proto-homogeneous subspaces of a quaternionic vector space. I would like to point out at this stage that the definition of quaternionic Keller angle does not imply that the canonical basis that we have here is constant. In fact, even if a space has a constant quaternionic Keller angle, this means that these numbers here do not depend on V, but this canonical basis used to define the Keller angle does depend on V in general. And this is a simple example that can be used to show that. So if we multiply a vector, a non-zero vector, by the imaginary part of the quaternions, this produces a three-dimensional vector subspace of our quaternionic vector space. It has constant quaternionic Keller angle, but there is no canonical basis that can be used to produce the Keller angles, which means, so equivalently, in the previous definition with symmetric bilinear forms, this means that although the eigenvalues of that symmetric bilinear form do not depend on the vector, the eigenvectors do depend on that vector. Okay. So our first step to address the classification problem of proto-homogeneous subspaces in quaternionic vector spaces is to exploit the fact that they have constant quaternionic Keller angle. This allows us to define the following smooth distribution. For each vector v in our subspace, we define the following subspace. We take all possible complex structures in the quaternionic structure of Hn, multiply V by this complex structure and project onto V. It's easy to see that this vector here is orthogonal to small v, because when we take inner product with small v, this projection does nothing, and J is skew symmetric, so JV times V is 0. So this means that this is orthogonal to V, and since we are we are considering the sphere of V, this is precisely this means precisely that these vectors are tangent to the sphere of V at the point V, and these spaces always have the same dimension because of the assumption that the Keller angles are constant. So basically, the dimension of delta V is the number of angles here that are not pi over 2. So, in summary, this means that delta V, or delta, I should say, defines a smooth distribution on the sphere, on the unit sphere of our space V. But it was proved by Steenrod that not any such distribution is possible in spheres of arbitrary dimension. In particular, for example, if our space V is even dimensional and has dimension greater than 5, then its sphere is even dimensional, and it follows from Steenrod's theorem that no trivial distributions can be defined on an even dimensional sphere. So this means that the only possible distributions are the zero distribution, the trivial distribution, or the whole distribution, the whole tangent space. But recall here that the dimension of this space is the number of angles that is different from pi over 2. So the dimension here is at most 3. So it cannot be the whole distribution, the whole tangent space. So it has to be trivial, which means that all angles are pi over 2. In the case that the dimension of V is 2 mod 4, it means that the dimension of the sphere is 1 mod 4. And it follows from Steenrod theorem that distributions, continuous distributions in these spheres can only have dimension or codimension 0 or 1. Since the dimension is high enough here, we can only have distributions of dimension 0 or 1, which corresponds to Keller angles pi over 2, pi over 2, pi over 2, or one of them is not pi over 2, which is contemplated in this possibility. And in the case that the dimension is 3, this means that our sphere is 2-dimensional. So since this is at most 3-dimensional, the whole tangent space can arise as a distribution. This is somehow a special case. And in this case, we have 2 possibilities. Either we have the trivial distribution, the 0 distribution, or a 2-dimensional distribution, which would be the whole tangent space. But the 2 Keller angles, so this can be pi over 2, pi over 2, pi over 2, or 2 Keller angles are different from pi over 2, but the 2 Keller angles must be equal, because if they weren't, then the corresponding eigenvector to each Keller angle would define a 1-dimensional distribution, and this is not possible by the Heribald theorem. So they both have to be the same, and this is somehow summarized by this condition here. So basically, we have somehow sorted out many cases. We have sorted out the odd-dimensional case, except for k equals 3, which is somehow special, and also the case 2 mod 4. Some of these examples were already known. So Keller angle pi over 2, pi over 2, pi over 2 corresponds to totally real subspaces. These are well known. 0 pi over 2, pi over 2 corresponds to totally complex subspaces, which are also well known. If we put phi instead of 0 here, this is also known. These are subspaces of constant Keller angle phi inside totally complex subspaces. And for k equals 3, 0, 0 pi over 2 is the example that I presented before, where the canonical basis varies from point to point. And all these 4 examples, or these 4 families, were known. So what remains to be done? Well, we have to address the case when the dimension is a multiple of 4. This is not sorted out here. We have to study the case of dimension 3 when phi is not pi over 2 or phi is not 0. And then the rest is basically sorted out by previous knowledge and the Steenrod's theorem. So these are the 2 cases that we have to address: dimension 3 and dimension a multiple of 4.
Can I ask another question? Sorry.
Yes.
Okay, but in all the other cases which we now know due to the Steenrod's theorem, does the Quaternion Keller angle determine the proto-homogeneous subspace uniquely up to SP1, SPn?
Sorry, if the Keller angle determines?
Does the angle, so for example, in these cases which we now have settled, does the angle determine the subspace uniquely up to SP1, SPn?
Yes, that's the case, because it was proven in a paper by Berndt and Brook that in these cases you can find a basis which basically depends only on phi, and this depends also on SP1, SPn. So yeah, everything is determined. You can give an explicit basis, and the only thing that can change there is that you move it around with SP1, SPn, but not.
But it's only true for these angles, right? It might happen for some other angles that you can have non-congruent subspaces with the same Quaternion Keller angle.
Yes, exactly. Actually, this is what I am going to explain.
Oh, okay, sorry. Okay.
Yeah. So for all these examples, yeah, the Keller angle determines the subspace that, well, the Keller angle and the dimension, of course.
Yeah, sure.
Yeah, and but there are other cases in which there are two non-congruent families, and one of them is actually the case of dimension 3 with phi pi over 2. So there are exactly two non-congruent families which depend on a sign here, this plus minus. So there are two non-congruent families, and the same will happen in dimension multiple of 4. But these are basically the only two possibilities that can arise. So either you have a plus or a minus, then you can move everything around with SP1, SPN, but these are the only two congruency classes. Okay. And I am not particularly interested in how we do this and what is the basis. I think it suffices to say that one can work out explicit form for a basis of these spaces, except for this plus minus sign. Depending on whether it is plus or minus, we have non-congruent families, except for phi equals pi over 2, I think, or phi equals 0. I don't remember exactly, but except for one degenerate case, these two examples are non-congruent. Also, phi has some restriction, which I haven't written here, but I think it is not particularly important. And the way to obtain this result is basically to study the symmetric bilinear form that I defined before, use the fact that it diagonalizes independently of the vector, work out the equations, and after some work, we get this basis, which somehow solves the problem. Actually, the most interesting case is not dimension 3, which can be somehow handled by doing explicit calculations. The most interesting case is when the dimension of V is a multiple of 4. Some examples were already known, like quaternionic subspaces, which are, of course, of dimension multiple of 4, and complexifications of spaces of constant Keller angle. And in a previous paper with Miguel Domínguez-Vázquez, we found other examples of dimension a multiple of 4, but with Keller angles which were somehow weird, at least at the time. And this is basically what we generalize in this construction. Well, in the construction that I am going to present now. So, recall the situation now. We have a proto-homogeneous subspace whose dimension is a multiple of 4. Since it is proto-homogeneous, it has a constant quaternionic Keller angle. And the first result that we use is the classification, or at least the description, of effective and transitive actions on spheres. This is attributed to Montgomery and Salmerson and Borel. And using the result, we can basically prove that this Lie group, the normalizer of V in SP1, SPN, can be assumed to be contained in the SPN factor. So somehow the SP1 factor is not relevant for this construction. And this is actually, it has a very important consequence, which is the following. If you think of the SP1, SPN action on the quaternionic vector space, SPN is basically action by quaternionic isometries, and the SP1 factor somehow moves the quaternionic structure around, so it moves the canonical basis. So the fact that this group is contained in the SPN factor means that the canonical basis that we have here in the definition of quaternionic Keller angle remains constant. This can only be proved if the dimension of V is greater or equal than 4. It doesn't work in dimension 3, as it shouldn't, because we have a counterexample, as I showed you before. But under the assumption that our subspace is proto-homogeneous, the classification of effective and transitive actions implies that the canonical basis that is used in the definition of quaternionic Keller angle is the same for all vectors V, not only the Keller angle, but also the canonical basis. And this is basically crucial in the rest of the proof. Give me a second. Okay, and why is this? Okay, so the situation now is we have a proto-homogeneous subspace whose dimension is a multiple of 4, and there exists a group containing Spn that acts transitively on the unit sphere of V. So the Sp1 part we can forget about if we want. This means that the canonical structure realized in the Keller angle is constant, and therefore we can define a complex structure on V, which is basically taking the canonical structure considered above, we project onto the subspace V, and we normalize it so that it has the appropriate length. This, as I say, defines a quaternionic structure on V, and therefore it induces a Clifford modular structure on V. Clifford modular structures have been classified, they have been proved to be semi-simple, so the corollary that we get is that we have an H-orthogonal decomposition of our subspace V as a sum of modules, all of which have the same constant quaternionic Keller angle. So this is basically the crucial step in the study of subspaces of dimension multiple of 4, because it reduces the problem to dimension 4. That's basically it. And what happens in dimension 4? Well, it's pretty much a study similar to what we did in dimension 3. There are some examples which were already known, complexifications of subspaces of constant Keller angle, but then we have to do a somehow case-by-case study using the symmetric bilinear form that defines the constant Keller angle. We have to do some calculations, impose that the condition that the spectrum is constant. But at the end of the day, we can define, or we can find a basis of this space V, which determines it in a one-to-one fashion, except that there is a choice of sign in one of the formulas. Okay, so there are some vectors satisfying certain conditions, and here there's a plus or a minus, here there's a plus or a minus, and what we have been capable of proving is that depending on whether it is plus or minus, we get something different, and by different I mean non-congruent. So for a fixed dimension and the fixed constant quaternionic Keller angle, we always have, at least in the non-trivial cases where angles are pi/2 or so on, two non-congruent types, which we call V plus and V minus. And since we have explicit basis for all our proto-homogeneous spaces, we can derive a classification result of cohomogeneity one actions. The classification is not written here explicitly because the bases are not so easy to describe, and well, they are not so easy to say exactly what they are. So we decided to write in the paper just the moduli space, and it can be described like this. If we have a cohomogeneity one action on a quaternionic hyperbolic space, it's either the holosphere foliation or the foliation by geodesic spheres. Well, not the foliation, but the action of by geodesic spheres, so the action of the isotropy group, or tubes around a totally geodesic complex hyperbolic space. And then a huge family of examples, which is related to Bernd and Tamaro's construction, and which was basically what I tried to explain during this talk. which is somehow related to the classification of proto-homogeneous subspaces of a quaternionic vector space. Some other examples which were quite well known appear here. So, for example, tubes around totally geodesic quaternionic hyperbolic spaces of lower dimension are included in this part. Also, the solvable foliation is included here because we just take V to be a line, or equivalently, W would be a hyperplane here, and this would be trivial. But then, as I explained, there are many other examples. These examples, the congruency classes of these examples depend on the dimension n of the ambient space, the dimension k of the subspace V, and the Keller angles that can arise for these particular dimensions. And we explicitly say for each k and each n what are the possible families, the possible Keller angles, and so on. But this is a rather complicated table that I am not including here. If you want, we can discuss a little bit further. But I think this is basically the conclusion that I wanted to show you. And just as a byproduct of not the theorem, but our study of proto-homogeneous hypersurfaces, we noticed the following interesting property. Assume that we have fixed a constant quaternionic Keller angle. Here it should say constant quaternionic Keller angle. For some spaces of dimension 4, we saw that there are two possible congruency classes. These two are non-congruent. So we can take a direct sum of these two families, where the number of B pluses and the number of B minuses is greater or equal than 1. This implies that V is not proto-homogeneous, and the reason why this is the case is basically because V plus and V minus are not congruent. But V still has constant quaternionic Keller angle, which is the same as V plus and V minus has. If we take the Lie algebra, basically the same thing that appears in Berta-Marius construction, so we remove from G2 alpha this subspace V, we can prove the following. This is a homogeneous submanifold. The orbit through the origin of the group whose Lie algebra is Digus one is a homogeneous submanifold, but tubes around it cannot be homogeneous because V is not proto-homogeneous. However, tubes around it are isoparametric. This is a general result. Whenever we have a Dirac-Ricci space and we remove something in the orthogonal complement of the kernel of the nilpotent part, this is isoparametric. This was proved in a paper, in a previous paper with Miguel Dominguez some years ago. And it was proved in that paper that these tubes have constant principal curvatures if and only if the generalized Keller angle of V is constant. In this case, the generalized Keller angle is what we call here the quaternionic Keller angle, but this can be done in any Dirac-Ricci space, in particular in the quaternionic hyperbolic space. We can build, at least when the dimension of G alpha is high enough, hypersurfaces which are not homogeneous but are isoparametric and have constant principal curvatures. These are somehow the third set of examples with this property. There are examples in spheres. In that case, isoparametric and constant principal curvatures are two equivalent concepts. And there is a further example in the quaternionic Cayley plane. And this is the third family of examples, but the original thing in this situation is that this family is uncountable, whereas in spheres and the Cayley hyperbolic space, it was actually finite for a fixed dimension. So here for a fixed dimension, we have uncountably many examples. And this is basically the end of the talk. I just would like to point out that today is the 4th of May. So I would like to say goodbye by wishing that May the Force be with you.
Thank you, Carlos.
Okay, thank you.
Does anyone have any questions? Can I ask something?
Sure.
So first of all, just to make sure that I got it correctly. So in the case where V has dimension 4, so it was the last basically case we considered, and we induced kind of a separate, maybe new quaternion structure in V and said that it was a Clifford 3 module. So yeah, this decomposition, when we say that, okay, we can decompose it into irreducible summons, CL3 summons. Do I get it right that we know that each of them has quaternion dimension 1, because something like CL3 is a simple central algebra, so it has only one representation, and it happens to be just H.
Yes, yes.
Okay, so this is precisely the reason. Okay.
Yeah, so this comes from the classification of Clifford module structures.
Yeah.
And yeah, exactly.
Okay, that's great.
There are actually two possibilities for CL3 Clifford module structures. So what they call the delta plus and delta minus. Yeah. So, but yes, all these representations are semi-simple, and the irreducible factors are 4-dimensional or of dimension quaternionic dimension 1. Yes.
And this and so this delta plus and delta minus, do they correspond precisely to what we call V plus and V minus?
Not really, I think. No. No. So this can, I think it could be related, but in principle, it doesn't have to do with that. It just has to do with the two possible Clifford representations, and the other thing has to do with well, some choice of sign that we can do when we study the symmetric bilinear form. But yeah, in principle, they are not related, I think.
Also, I wanted to ask, is there any insight into how you prove that? So for example, here, when V has dimension 4, you found these examples where you have two different options for V with the same Keller angle, but which are still non-congruent, right? That's what we call V plus and V minus. How do you prove that they're non-congruent? Is there any idea behind it?
So the idea is that you have your basis, and so you pretty much can move things around so that the complex structures are the same, except that so you can fix J1 and J2, but then J3 can be plus or minus depending on which in the case you have. So I don't know how to explain this correctly. So you have like a choice of orientation.
Oh yeah.
Yeah. So.
Oh, and this you mean the J1, J2, and J3? You mean the canonical basis for the quaternion structure, right?
So the thing is that in one case it's J1, J2, J3, and in the other case it has to be J1, J2 minus J3.
Okay, I see.
So somehow you have the two spaces. You have the basis. You move things around so that part of these things match. But depending on some orientation, you cannot arrange things so that everything is exactly the same, but there is a minus somewhere. So there is this orientation which you cannot solve, and this orientation is what determines the plus or the minus.
I see.
Yeah.
Okay, thank you. And just maybe one small thing. So in this last, I think on your last, or maybe I think it was the next slide, where you say that we can take the sum, direct sum of B plus, and also I made the next any direct sum of B minus. So do I get it right that what happens if you take this several V pluses and several V minuses, but you're unable to take the direct sum because they kind of intersect?
Oh, but recall that so each V plus and each V minus is in a different HN somehow.
Oh, so we're taking the direct sum of HNs as well.
Yeah, so recall that the composition is H orthogonal.
Oh.
Yeah, so each V plus is containing H4, basically. This is, I think, the smallest HN that you can fit it into. So each one is containing an H4, but these H4s are orthogonal to each other. Yeah, they cannot intersect because it is an H orthogonal decomposition.
I see. Okay, thank you.
Yeah.